data. Burkhard will support this claim in the talk with examples in which students struggle to come to valid conclusions from their own data. Talk will then discuss the development of a model which bring measurement uncertainties into classrooms and covers all relevant content for high school students. Professor Priemer will show us how the corresponding learning environment, that's part of the development, which his group has made, how they look like. Coming to the speaker, Professor Priemer is a faculty of physics education. He began his career as a high school teacher in mathematics and physics and received his PhD in 2005 for his work on the use of internet to learn physics. After holding a position as an assistant and as a full professor in Bochum, Germany, he accepted an appointment at the Humboldt-Universität, Berlin in 2012, where he currently works. Over to you, Burkhard.
Yes, thank you very much. It's a pleasure to talk to you, to talk to a lot of people about the things we're working on. So thank you very much for inviting. Let me share my screen and let me go through the talk. We're not that a big group, so if you have clarifying questions or things, just just let me know and we can talk about it. But of course, there will be enough time for a discussion after the talk. Okay, let me share the screen. Let me begin with the presentation. I hope you can see the presentation right now and how this works.
Yes, it's visible. You can go ahead.
Fine, yeah. Your measurement uncertainty, we're looking at this from a physics education perspective for quite a long time because we're convinced that this is a very, very important topic, and it's a topic that is, however, neglected, at least in Germany, in school education, especially in physics education. And our aim is to change that. And let me give you a couple of examples why we think this is a relevant topic. Let's see. Well, yeah, this is one example. When you look at 3 thermometers and air humidity measurements, and there are 3 same models, 3 different measurements instruments of the same model, but they show different results when you look at the temperature and the air humidity. And this is our very easy measurements. And when you present this to students, they're kind of surprised. How come that different measurement instruments show different temperatures, or air humidities should be the same? So I've talked to students, I say, this is strange, something is wrong with the instrument. So this is something they see in their everyday life, that things sort of vary between measurements. We looked at a couple of justifications students give when they work with experiments. This is one of the experiments we did. You can see on the right-hand side, there are 3 foam cubes and they have different sizes. And what we did is that we measured the temperature inside of these foam cubes. And as you can see, these measurements can be made in the different foam cube sizes. And before the experiment, we asked the students, what do you think, what influences the thickness of the material on the temperature you measure inside? And 80% say that, yeah, the thicker the material, the higher temperature, which is a preconception students have all over the world. This comes from students' everyday life experience when they put on clothes, which is okay because that's what they experience. But what we what I think is very interesting is that still 50% of the students stick to that answer, even though they went through an experiment they did by themselves. And this is a sort of surprising, because we as a physics teacher think, well, if we show them enough evidence that their preconception is not true, they should change. But very often they do not. This is interesting. And then we ask students, well, how come that you still think that the thickness of the material has an influence? And I say, yeah, because this is one answer a student gave, because in the smaller cube, it was 22.1 Celsius or 22.2. In the bigger one, it was 22.3. So it's clear the temperature rises with the thickness. This seems like a pretty logic answer for someone who doesn't know that, that there are uncertainties in the measurement of the temperature and that the values or the measurement values can vary. This is another example. On the right-hand side, you can see part of a pendulum. This is the string of the pendulum. This is the bob that, you know, swings in that direction and back. We did an experiment where they measured the displacement and the influence of the displacement on the time of oscillation. This is the light barrier. It doesn't have anything to do with this certain experiment. And what you can see here is that this is the displacement in centimeters, and this is the time of oscillation, and this is the measurements the student made, and this is what his complete result in the end is. And this is again an example what shows that students somehow don't know how to bring all these measurement points together to make a valid conclusion. The simple pendulum is another example. When you look at the influence the mass of the pendulum has on the time of oscillation. We've asked the students, almost 1,000 students right now, what they think, what's the impact or the influence of the mass of a bob on the time of oscillation. And again, this is a preconception a lot of students have, that they think, the heavier the mass, the faster the pendulum swings, which is a preconception that is well known, which is in a way fine as well. But again, we found out that even after the experiments, still 50% of the students keep this idea, even though they were confronted with an experiment they did by themselves. So this is again very interesting. How come that for us as a teacher, the hard evidence that the preconception is not true, how come that the students still stick to that? And these are the data one of the groups of the student groups collected. On the right-hand side, you can see the table. Mass is the German word for mass. So this is one mass, for example, of 50 grams. This is another mass, for example, like 100 gram, or a third mass, for example, 150 gram. And these are repeated measurements they made for, I think, 5 oscillations each. And then you can look at how close the time of oscillation is. This is the time of oscillation on the diagram, showing for one mass the error bars, and for the second mass the error bars. And as you can see here in this diagram, it's pretty obvious that the mass, at least for these 3 examples, doesn't have any influence on the time of oscillation. But when we ask students, well, why do you still think the mass has an impact on the time of oscillation, even though you have this data? They say, well, I think it's not accurate enough. And we asked them, why is that not accurate enough? And they were sort of surprised when they do repeated measurements, as you can see, that the values all differ, that they don't get the same values for every measurement. And they concluded, well, if this is the case, if I do repeated measurements and always get other values, I don't think that my experiment is good enough. So, they sort of ignore their data and stay with what they had. So this is another example. We can see that students have misconceptions about measurements, and students come to, very sadly, to very wrong conclusion, even as though their data is very, very good, as you can see in this diagram. So this is a bit, well, we can see that we have to do something. So what will this small talk will be about? I think it's well known that practical work with measurements is very important when we do teach science. We have to show them experiments, and we have to use data to show how some laws in physics were designed. And capturing and discussing measurement uncertainty is essential to assess the quality of measurements. Well, if we are honest as physicists, if we don't know how good our data is, we don't know what kind of uncertainties our data have, we cannot make any conclusions. Measurements, uncertainties, they're inevitable. You always have them, even with the best experiments, and their estimation is needed to draw conclusions from empirical data. That doesn't mean that you always have to address measurements uncertainties when you do an experiment in schools. There are a lot of experiments we can do just to show students the phenomena, or to show them that things can be measured. Then you don't need any discussion of uncertainties. But, and this is my claim, whenever you use the data to make conclusions, so whenever you need the data to show something quantitatively, then you should, at least in a certain way, discuss the uncertainty of your data. As our small studies show, that students come to wrong conclusions, and I put it that way, even though they argue correctly from their perspective. If you don't know that values vary, if you don't know that measurements always have uncertainties, it's not the student's fault that they simply look at the data and come to conclusions, to mathematically correct conclusions. This value is higher than that one. Even though that the physics behind us remains hidden. I guess when this is the case, we're in the need to talk to the students about the quality of the data. But when we look, this changed a bit, but when we look at typical physics classes, measurement uncertainty are often neglected in teaching practice and school curricula, especially in lower secondary education. By saying this, and this changed a bit in Germany. So there are new standards right now from colleagues that where there measurement uncertainties included right now, which is a very, very good thing. I'm very thankful for the colleagues who put this in the German standards. So things change slowly, but it takes quite a while until it reaches the school practice. So what we see is that students have little knowledge about measurement uncertainty. And I think a lot of students, even physics students, take the discussion of measurement uncertainty as one thing they have to do without thinking about it. But I think it is our task as physics education researchers and practitioners to show that it is highly relevant, and that's a very interesting topic to talk about. Okay, what will this talk will be about? When given enough time, I want to go with you through those bullet points. What is the relevant content when teaching measurement uncertainties? I'll quickly like to introduce you to sort of model we've worked on. So we have a sort of a didactical reduction that puts together all those things we think are important. And then I will give you a very, very short insight into how we are at the moment working on to find a good measure to quantify measurement uncertainties without using standard deviation, which is very hard for students to understand, especially in the lower classes. We did some couple of studies where we looked what do students do correct without really thinking about it, so a sort of intuitive understanding of measurement uncertainties. And then, of course, I'd like to show you how competences can be accessible and measurable. This is more or less a test we've worked on for different aspects of measurement uncertainties where you can evaluate students' competencies. And we've worked on interventions and looked at their effectiveness. Yeah, I'll go through all that very quickly only, but go ahead and ask questions in between or after the talk if you need clarifications. Well, first we go through the subject matter model. When we started thinking about measurement uncertainties, we looked at, well, what's the content? What is the relevant content? And we're set together for a couple of years, to be honest, and looked at high school textbooks about measurement uncertainties. And we went and then to experts in measurements and showed them our model where we sort of structured and grouped all the content we found relevant in textbooks and web pages. And after that, we looked how we can make this accessible to secondary schools. And we talked or we made an evaluation with about 100 teachers that helped us to come to a model that can be used in secondary education. And this is the model contains 4 dimensions with subdimensions, and I will just give you a quick overlook of that. We've published it in detail, but just to let you know what's the content we're talking about when I talk about measurement uncertainties. We talk about sources of uncertainty, and we talk about distinguishing uncertainty from error. I'm going to say a couple of things about that in a moment. We have the dimension of how to handle with uncertainties. So what's your measurement objective? How to put down the result of a measurement? And the third dimension is the assessment of uncertainties. This is mainly a direct measurement when you can measure one single quantity, or indirect measurements where you have what is usually called the propagation of uncertainty, where, for example, more uncertainties more quantities are measured with uncertainties, and you make a conclusion about the third quantity, and then you see that the uncertainties propagate. And the conclusiveness, more example, what can you do with that? How can you judge the reliability of a measurement? And how can you compare a result with other measurement results or with a sort of reference value? And the third and the last dimension is how you can draw or how can you fit data into a straight line, which is often done in schools. That's why this is concluded in that. How can you do that? So this is a very, very quick overview of the model. Just let me give you an example for that. Imagine you have the experimental task to determine the focal length of a lens, and you have some sort of reference value from the manufacturer, say let it be 13 centimeters. And yeah, this is how the experiments may look like. Probably most of you are familiar with that. And let's have a look at 2 possible results. One is 12.9 centimeters plus minus 0.8, and the other is 12.2 plus minus 0.1 centimeters. This could be the result of 2 measurements. And what's the difference? The first one has a very large uncertainty, which is expressed in this term here, the 0.8. So this is very, very comparatively large. And it has a very small error. So the error bar is the distance between the measurement, the best value I have here, the measurement, and the reference value. So this is, you can say this is a large uncertainty with a small error. And yeah, you can call this accurate, but not precise. But it can be the other way around as well. You can have a very small or a comparatively small uncertainty, like shown here in the diagram, and your value 12.2 can be quite far away from the reference value. So this is expressed as error. So you can have a small uncertainty and a large error. And this is when this is the case, we typically, as physicists, look at some sort of systematic area or systematic uncertainty that led to this result. But this is something, and this is my point, that can be easily taught in schools as well, to differ between an error and the uncertainty. And another thing I want to quickly show you is that you can do uncertainty propagation and with very, very little mathematical complexity. For example, if you have sums and differences of quantities, it's easy just to add or subtract, or if you have sums and differences between different quantities. What you can do is you just add the uncertainty components. I mean, this is pretty conservative because it's a maximal estimate of the uncertainty, but it's easy to do, and it's enough for students to learn how to deal with that. If you have products and quotients, then the rule is add the relative uncertainty components. This is an example. If you determine the electrical power using the voltage and the current, and you can look at the relative uncertainty. The relative uncertainty is very easily calculated. When this is your measurement value in volts, 8.0 volts, and this is the uncertainty, 0.1 volts. You just look at how big this is percentage of the 8. So that will be about 1%. You can do this for the current as well. And then you get a result of 7%. And then you simply add 1% to 7% because this is the multiplication, and you end up with 8%. And you can calculate it back. What's the absolute uncertainty? So you come very, very easy to weigh how to quantify the uncertainty for physical. For any pretty easy physics content, like multiply quantities, or you add them, or you have quotients. So this covers, I think, for a lot of concepts and a lot of content in physics. And it's easy, you just need percentages and to add percentages. So so this is one way we can teach this in high schools, and without having the complexity of calculating standard deviations and stuff, without having that hiding our main argument that we need to find out if we measure voltage in the current. We need to find out how good is our results when we want to know what the electrical power is. Okay. And another thing that can be shown in high schools, or even in schools, very easy, is how can we compare measurement results. This can be done graphically, of course, can always be as well be done mathematically, but all you have to do is you look at overlapping uncertainty intervals. So if this is your measurement 1, the best value, a mean value, or whatever, and this is your uncertainty interval, you just compare those two uncertainty intervals. This is the second measurement. And whenever these uncertainty intervals overlap, we can say the measurements are in agreement. They're close enough. There are enough values that both of the intervals share. If they're not overlapping, which is the second example here, then they're not in agreement. So there's a significant or difference between the two measurements. They're not agreed. That obviously didn't measure the same thing. This is, again, of course, you can look at it mathematically and find out if the intervals overlap, but you can put this in the graphical explanation as well, which makes it very obvious for high school students to work with. Okay, so if there are any questions here, just go ahead and ask them. But I want to show you that the content of measurements uncertainty is of course very complex, but they can be reduced in a way that it can be taught in high school physics. Okay. Well, then I can continue. I want to show you what kind of research we did. One of the things we're looking at the moment is what is the good measure for uncertainties? As a physicist, we usually use the standard deviation or the standard error of a mean value, for example, but this is complex for high school students to understand. So we have to come up with another idea how to measure the uncertainty, which is less complex. Below you can see on here this diagram again. You have a measurement value, you have a reference value, and so this is the measurement, the uncertainty interval, and we need somehow to quantify this. How can we come up with this? And what, like I said, we usually in physics use the standard deviation, but there are more or easier measures. For example, you can take all your measurements and look at the minimum and the maximum, and say, okay, the span width, I can use that as a quantification of the uncertainty. Or we can, look at all our measurements and exclude extreme values. We can do that. We can use the middle 50% of all the measurements we collected. We can look at the mean absolute deviation. So we'll look at the mean value and look at all the other measurements and then, calculate their distance, and then we take the mean distance. And of course, we can take the standard deviation. All those measures, of course, have different complexity. Being the easiest is just to look at the minimum value and the maximum value of all the measurements, and calculate the students the difference between the minimum and the maximum value. This is very easy mathematics. However, what's the best? What's the best for school education? And of course, it depends on the age level. But what we looked here at the diagram to the right, I know this looks sort of complicated, and in a certain way it is. But what we did is we looked at on the x-axis here is the number of measurements you have a subsample. Usually, when you were in school, you have 10 measurements or 6 or at most 20. So this is here, and on the y-axis, we see the deviation of a measure of an uncertainty measure to the standard deviation. And this is the standard deviation. If we take this as a sort of as a reference for a good measure for the uncertainty, we can look how the other measures like the minimum, maximum, or just excluding the extremes, how they differ from the standard deviation if we take this as the gold standard and to calculate the uncertainties. And as you can see, if you use the minimum, maximum, and span width, the more measurements you get, the far away this gets from our standard as a standard deviation from the gold standard. But it's interesting to see that if you just exclude the extremes and you have 8 measurements, you get pretty close to what the standard deviation brings. So with this diagram, there's a simulation, Monte Carlo simulation behind it with quite a lot of data values. What you can take out of this is some of even the easier to calculate measures to quantify uncertainties. They can still be quite good, pretty close to the standard deviation. So as a teacher, you can start with using the minimum maximum method because it's so easy to calculate. And then you can, the further it gets complicated, the closer you come to the standard deviation. So there are a lot of different measures you can use as a teacher to quantify uncertainties. I think this is what you might want to take out of the slide. And another thing is, what's the intuitive understanding of students, of measurements? It's amazing when you ask students that are not very familiar with uncertainties and just give them 2 data sets like this data set here, measuring the density, and you give them these values and that values and ask them, well, what do you think is better? And they don't know a lot about statistics. They still see that still say that they prefer less variance and they prefer higher sample sizes, and they say, well, more decimal places is always better. So they have some sort of good feelings about what it takes to have good measurements. But when you ask them to justify their answers, they don't come up with any good scientific reasoning. So we can say, yes, they have some idea about good values or good measurements, but they cannot really reason good for that, which can lead them on the wrong path as well. This is a result of a study where we wanted to find out if we give students better data meaning more precise data when it comes to the number of decimal places. We wanted to find out if you give them good data like group C here, with a high number of decimal places, if they come to better conclusions. And what they had to decide, the students, was if you have a free-falling object that falls down and you have a ball that rolls down a ramp and then gets launched. And the students were asked to compare the time it takes to cover this distance for the 2 cases. And this is the data we gave them. And the thing is that there's less variance in group C. They get for the free fall and the launched, and but there are only 2 decimal places for group A, but there's more variance, but students don't see it. And when you look at the results, we have to say that the better the data was, the more decimal places they had, the worse were students' conclusions when it comes to the physical context. And the sad thing about that was that students were simply incapable of dealing with the uncertainties. So they don't know how to deal with all those decimal places, and they were confused by it. So this again shows that we have to do something about that. And what we did is, because we were so interested in the topic, and we did quite a lot of studies, we thought, well, in a way, we need measurement instruments to find out students' competencies using measurement uncertainties. And it took us quite a while to come up with a questionnaire, with a sort of test assessing students' competencies. And we used our subject matter model. I explained to you with the 4 dimensions, and it has in total 10 subdimensions. And we developed a scale for each of the subdimension and constructed the test and piloted this with 1,300 students. And again, now we do have a sort of instrument to measure students' competencies when working with measurement uncertainty and very different aspects of measurement uncertainties. To the right, you can see one example of the test, one example item. I can go back to that if you want to, but right now want to continue. What we did as well, we not only saw students' difficulties and were able to describe what these difficulties are, but we're interested, of course, if we can teach students at least parts of measurement uncertainties because it's not done in schools. So we have a prototype of a digital learning environment that deals with how students can compare the measurements of two measurements using measurement intervals. It's about comparing data sets. Right on the right-hand side, you can see a screenshot. It shows the learning unit. It has different steps, 5 steps, where students are guided through. It has a lot of examples. It has multiple choice questions and other interactive elements where they can look at the data and see how the more data you get, what kind of measurement, what impact this have on the measurements and the uncertainties and all that. So that leads students through at least some of the aspects of measurement uncertainties. And it takes only 45 minutes to go through, so which is quite a okay time to work for the students. And even with that really short introduction to it, or short learning unit, we see that students shift from point understanding of a measurement to a set understanding. Point understanding means that a measurement is just the one single value, and set understanding means that there's an interval to every measurement. It's not only the value I've got, but it's an uncertainty interval around it. And what we could see as well, that students from 14 years on benefited from this learning environment we constructed. I'm not saying that they have a complete and very, very good and long-lasting understanding of uncertainties, but after a 45-minute instruction, this is of course not the case. But what we could see is that students' competencies increase, even though this is only very short instruction. This is more precisely looking at how students worked or how students argue when they have to compare data sets. What you can see is on the left-hand side, that is what kind of quantity they use when they get 2 data sets of, let's say, 6 or 10 values each. How do they work out if they, when they have to compare them? And what a lot of students do, and this is coded in here, they looked at pairwise comparisons. So if you have 2 data sets of 6 values each, they take pairs of one data set each and compare these. This is what's called a pairwise comparison. The dark blue one are the pre-test results, and as you can see, this is one of the standard they do. They don't really know how to deal with the whole set, but they just take pairs of their values and compare them. And this dramatically changes to using intervals after the learning environment, which is a good thing. So the quantity they use to compare seems to change. The whole idea of using intervals was introduced to them, and they very, very competently use that. And what values do they? This is the quantity they use, but how do they compare them? What's the criterion they use for that? Usually they take what's bigger or what's closer before they go through a learning environment, and after that they shift to looking at overlaps and intervals. And this is very close to really what we do as physicists when we use intervals, and we look if they do overlap, like I told you before. So what this shows in a very small setting, of course, that it's not so very hard to teach basic concepts of measurement uncertainties. So, okay, I'm quite good in time-wise. So what are my final conclusions? I think if we use empirical data in schools, and we use this data to draw conclusions, we have to look at the measurement uncertainties and do not hide them, and do discuss them with the students and see what kind of conclusions we can draw from the data. We know as well pretty good right now that an intuitive understanding of uncertainties may help once in a while, but it's not sufficient. That can lead you on the wrong path. Usually, I mean, this is what the model wanted to show you, that some concepts of measurement uncertainties, they can be taught with very, very simple mathematics, which is a good, I think, a good result when it comes to teaching this to school students. And I did as well taught measurement uncertainties to 6-year-olds in Germany, 6 and 7-year-olds. Of course, you don't use mathematics; you just compare the size of the values. But still, they already grabbed the idea that if you repeat a measurement, it's not surprising that you don't get the same result. Some of these concepts do not take so very long to understand, and you don't need a whole curriculum. You have to rush your students through before you can start doing that. You can. Sometimes it takes just maybe 5 minutes, 10 minutes, or 20 minutes break and discuss uncertainties, and you can include this in your regular physics lessons. Yeah, like I said, some of the concepts are easy enough to grasp for kids as young as 6-year-old. So yeah, this was a quick, I know that was very quick for you. I've rushed you through all this, but yeah, don't hesitate to ask questions or ask for clarifications or give you comments. Very much welcome comments on our work, and don't hesitate, please. Well, thanks for listening so far.
Thank you, Burkhard. Please, if you have questions, either type it in your chat box or like raise your hands. I have a yes, there's a question in the chat box, but before that, I have a quick clarification. So you mentioned, you showed that digital learning environment you developed, right?
Yeah.
Yeah, so one problem requires 45 minutes to solve. Like, what is the, like, can you elaborate a little more on the nature of problem? I mean, it was written in German, so I couldn't, like level 1, level 2, level 3. It's the same problem which has multiple levels and takes 45 minutes to complete. And what are the...
Yeah, it's not a special problem. It's the concept. How can you compare two data sets in general? And the learning environment shows you different examples. Like, one example is a skateboard rolls down the ramp, and you have two different skateboards, and you want to compare the skateboards if they're the same or not, if they have the same rolling abilities. And you make certain measurement how long it takes them to roll down the ramp. This is one example, but the learning unit is generally about the concept of how can I compare two data sets, how to calculate the mean value, how to come to a measurement interval for each measurement, and how to work out if the intervals do overlap or not.
Is that available in English? Is it accessible?
No, but we'll do that. It's just the work of a PhD student who just handed in his work, and he will defend it very soon. And we're going to translate it in English. That's for sure. And then we can make it. It's not accessible in German. If you want to look at the German version, it's accessible for high school teachers in Germany and for everyone all over the world, but it's still in German. But we can translate this in English as well.
Okay, thank you. So there's a question from Shirish and then Arnab. Yeah, Shirish, you want to go ahead and speak?
Yeah, sure. Yeah, it was really a nice talk. Thanks a lot for the talk. So just wanted to know from what age is this concept of uncertainty measurement is introduced to the students? I mean, at school, from which standard that you start with? That's the first question.
Yeah, I think the model is for kids like 14 years and up. This is the way it was constructed. Yeah.
Okay. So with them, you may start with something like range method or some simpler methods.
The model was, was reduced for kids in that age.
Okay.
Yeah, and it's published. The whole model in detail is published. So there are a lot of examples, and it's explained what each of the concepts and dimensions are made of.
Another question that I had was like, is it really difficult to convince teachers and students to use this uncertainties in their lab course? Or is it like a culture of using this analysis and teacher accept it comfortably?
I'm not quite sure if I really understand, but what we do teacher training, and we try to show them that it's very easy to calculate uncertainties, and that they can include this in their own teaching, because most of them remember, most of the physics teachers, they have studied physics, and they remember, that the Gauss propagation of error and stuff, and say, oh, this has nothing to do with what I do. And we do a lot of teacher training, show them, well, it's, don't let the mathematics stand in front of this very, very important topic. And so we're trying to make them more and more aware that this is a very useful concept. But I'm not sure if I understood your question.
Yeah, I think that was my, I think you have answered it. But so this uncertainty analysis, it's, I think it's very much there in your curriculum, right? So the moment you say lab course, so students are supposed to calculate that.
Yeah.
So maybe it is easier to convince or teach teachers to do that. Maybe some advanced methods or something.
Yeah. I think always when we really use the data to draw conclusions, and how we as a physicist, we will never draw any conclusions if we don't know about the quality of data. And why not tell this to children?
Yeah.
And then even if they have, I have an example where they really have bad data, very, very variances, but still, if we want to be honest, we can still use the data. And if we make an uncertainty analysis and come up with it, we cannot draw any conclusions from what we've got. This is still a good result. So we can look, wow, which quantity makes the most influence on the uncertainty? How can we reduce the uncertainty? How can we do that? And then we can start measure again, like we would do as physicists. So, but yeah, I think we have to be honest with our data, and if students collect the data, they have got to be honest with that.
Yeah, and just one more question. At say undergraduate level, or even postgraduate level, do the students follow some advanced methods of uncertainty analysis, like which are been nowadays very much given by JCGM or guide to uncertainty measurements. So like instead of talking about normal distribution, we should be talking about rectangular distribution. So that kind of a shift is it happening with the colleges?
I think talking about normal distribution is quite advanced. You can do this in upper high school and in university as well, but you can look at distributions, but I think there was something like standard deviation, and looking at how big is the percentage of the values between the boundaries of the standard deviation. This is something you can do in higher education or in high schools, but not from year 14 on. I think this is too complicated. I think we don't really need it. But when you look at the measurement of quantities, how to quantify measurement uncertainties, you can start with very, very easy measures. And if they do understand, okay, I have to look if intervals overlap to find out if measurements are in agreement. You can later tell them, well, we'll use another measure for uncertainty right now, one which is sort of better because we have extreme values, and they sort of influence my uncertainty interval very, very heavily. If we use standard deviation, we get rid of all those extreme values, which is good, which is what physicists do. But as this is you can do it in a cumulative way. You can start with easy measures and make them more complex, coming closer to standard deviation. But the concept, the idea behind it stays the same.
Yeah. Thank you.
Okay, thank you. Arnab, go ahead.
Yeah, I find that Vijay has actually asked one of my questions, analog versus digital, so I'll let him ask it. The question I had was, you said that it is very difficult to explain standard deviation to these high school students. So I'm just wondering, are these the typical high school students who are going to be appearing for their Abitur exam in a gymnasium, or are these sort of the more real school students or something like that who are not at that level? I mean, what level of students? Because I thought that by the time people are finishing with their high school, they would be familiar with standard deviation.
Yeah,
And variance and things like this.
That's correct. I was hoping that too, but the reality shows that it's often not taught in high schools, even not in Abitur. It's not that they were not able to understand it, but it's often not taught. And even, when students come to our institute to start studying physics, some of them don't even know what a standard deviation is. I mean, they can understand it, but if you look at students from like 16 years old or 14-year-old, they struggle with the mathematics. Of course, not all of them, that's true, but some really do. I'm not saying that you shouldn't use the standard deviation in high schools. I'm just saying that you can start discussing uncertainties without knowing what a standard deviation is. And whenever you like to, you can introduce that later.
Okay. And I had a question on analog versus digital, but Vijay Singh has written it very well in the chat, so I'll let him take it.
Okay, thank you. Vijay Singh, you can go ahead. Yeah.
Well, the question is basically, can you hear me?
Yeah, I can hear you. Yeah.
Okay. So do you look at differences in analog versus digital instruments? Say an old-fashioned voltmeter with a dial and a digital one. Do students trust the digital one? Are the instruments as reliable because they are digital? Or that is one question. And the other was, could you go over the plot of comparisons of the Minimax and the MAD, etc., with SD once again? Okay.
Okay, I think the first question is, what do I see? What are the differences between using a digital and an analog instrument?
Correct.
Yeah, I think they're both in use at schools. I mean, they have you take the last in a very easy way. You take the last digit of a digital instrument and use that as the uncertainty interval. However, saying this, a lot of measurement instruments, digital ones, they show the resolution of the scale is higher than the uncertainty. That means that some of the instruments are not as good as they look. Then it's not the case that the last digit, I mean, especially for time measurements, it's not the last digit that really tells you the uncertainty. A lot of instruments, easier stopwatches, are worse than the last digit. And analog instruments, you can use half of the difference between the two different, the finest grain level between the scales.
But is it necessarily so that they would trust a digital over an analog? I mean, and do you educate them about it? I mean, that the digital need not necessarily be more accurate.
Yeah. That's a good point. We say that the accurateness of an instrument. I mean, digital is not always better as analog instruments. This is definitely the case. Yeah.
Okay.
And the other question, you want to have a look at one of the slides again?
Yes. Yeah. Could you just?
Yeah, sure. I'll go back to. Yeah, let me go back to a slide here. Just give me a moment, and then I can share the screen again. So here we go. I think this is that one. You mean that one here?
Yes.
I'll make this bigger here. Yeah, this is pretty complex. Yeah, a very short explanation. Go ahead and ask your question again, please.
See, there's a standard deviation which you take as a reference or a gold standard, and the one with, for example, the Minimax, all the way above it, and then it keeps increasing.
Yeah, it does.
Is that because you're doing more measurements, you will get more scatter?
Yeah.
Or was this an actual study of, or was it a Monte Carlo simulation?
It was a Monte Carlo simulation.
Okay, it's a Monte Carlo simulation.
Yeah.
And why is that other thing zigzagging? I mean, the one with, I'm trying to read it. Why is it going up and down and up and down?
Yeah. That's the, if you take
Yeah.
the middle initial,
Uh-huh.
if you, this is just, you see 6 and 7, and then if you take away the middle 50%, it's not continuous, because the middle 50% changes with the number of measurements, of course.
Mm-hmm.
So that that can go down again. It deviates more, and then it gets better again. Then it goes down again, and so on. It keeps off the zigzagging gets, of course, smaller the more data you get, because the 50% is more. It doesn't change so much with the number of measurements you do.
Uh-huh.
In the beginning, you have a small number of measurements. The impact of just taking 50% middle is pretty big. The more data you got, the smaller the impact is.
Okay, I think I understand it too. Thank you.
Yeah, sure. Thanks for asking.
Okay, thank you. And Anvesh, please go ahead.
Hi, am I audible?
Yeah,
Yes,
I can hear you.
Yeah.
Fine.
Yeah, so I was just wondering, I mean, in all these your interactions with students, have you encountered a situation where students sort of get frustrated over the existence of uncertainties at all? I mean, maybe.
Right now I can hear. Can I hear your voice?
Yeah, you got muted, Anvesh, somehow.
Them completely.
No, not completely. I understood that you asked me if students can get frustrated about, looking at their uncertainties. In a way, yeah. In a way, yes. It's a sort of, it can be a sort of disappointment, because when they do not discuss uncertainties, they have, they're happy with their values, and then, they kind of fiddle with them, and they come to a precise result, and they're happy with that. And then you say, well, you're not as good as you think. Some of them, oh, wow, this is, if this is the uncertainty, what can I make? I cannot make the conclusion I want to make. So yeah, I'm sorry to tell you, but this is over the case. This is the problem that deals with every physicist, and this is the art of making good measurements. This is why we have those institutes that look at standards and norms, and they struggle to come to good things. And then then I tell them, that physicists can now measure in attoseconds, which is the millionth of a million second, and they have such precise measurement instruments that kind of understand what that means. Yeah, but yeah, that is the case. That can be sort of disappointing to find out how bad your data are.
Right. I have another question. I mean, you talked about standard deviation and all those things, but do you also try to give them an idea of like what is a 1 sigma error, what is a 2 sigma error, and what do they mean in terms of probability and all that? Do you go to that extent, or you just use that just as some index of the uncertainty?
Yeah, we do this in university education, but not in high school education. We don't look. It can be done in certain classes in the high school, where you can have a normal distribution and look at the sigma, 1 sigma, 2 sigma, and 3 sigma, and then you can discuss modern physics, like detecting elementary particles and stuff. What they do with the Higgs boson. I mean, what was the idea? But not in a regular high school class.
Yeah, sure. No, I was more curious about whether you go to any distinction between, let's say, they write a result as 12.5 plus minus 0.1, whether they get any sense of what this means in terms of the probability of the value. I mean, that it tapers off. As you go far away, etc., according to a distribution and all that. Do they get this sense, or they think that like it is like a broad range and it can?
No, they do. They do get a sense of it because when you discuss it, you take the span with that. There's a minimum value, the maximum value. They know that all the other measurements are in between. So this is quite conservative way, always to do the minimum and the maximum. And when we say, well, all those extreme values, they sort of they do exist, but they're not. They don't have to be over-evaluated. So when you say, well, let's take away those extreme values, take the middle 50%, then students know, well, we're skipping something off. There's a probability that you get a measurement that is in there, but that's smaller. In that sense, they do understand it. And when you make your interval smaller, that you kind of do not cover all possibilities, and but they see the value that they're so rare that's okay if we skip them, and then we get a smaller interval. In that sense, you can discuss probabilities. Yeah.
Okay. Yeah. Thanks. Yeah.
If there are no further questions, let's thank Burkhard for his nice talk and answering the questions and walking us through the different dimensions of uncertainty and the difficulties that students face at the high school level. So thank you, Burkhard, for your talk and for your time as well.
Yeah, thanks. It's been a pleasure. And whenever you feel that you have more questions, or if you want to have references or papers and things, when you want to dig into this, well, just let me know.
This assessment that you mentioned, that is publicly available, or?
Not yet, as well as just the PhD work that was completed in December. And so it's going to be translated and published as well. It's still in German.
Okay.
But, we have already a lot of people asking us if they can use it for their, for the practical work. And as it is at the moment, we only have this available in Germany, but we're going to change that.
Okay. Thank you once again. Thank you everyone for being here and being part of the talk.
Yeah, thanks.
Bye-bye.
Thank you.